Okay. Hi, if you're watching this recording, then unfortunately I started a few minutes ago, but we'll continue for you. I think one or two people are gonna have to watch this recording. Okay. Um, so where was I? Yeah. So the goal of this course is to learn what does a proof look like, and that in itself is actually really hard. It's pretty hard for someone without this style of thinking to be able to learn what constitutes a proof, and so that will really be the main goal. So the course is structured like this. A first handful of lectures will be like you can consider like tutorial, right? You'll learn the techniques. You'll get a toolbox, and then the rest of the course will be dedicated to having you guys write as many proofs as possible. So what we'll do in those lectures will be I will give you some object to think about. So for example, maybe I give you some definition of a graph, and some of you guys know what a graph is from computer science. And I'll say, okay, a graph has these properties, and there's this kind of graph, that kind of graph, and then you will try to write as many proofs as you can. And along the way, with greater feedback, you should try to refine your idea of what looks like a proof, what constitutes a proof. Okay. Any questions so far? And you can also just put questions in chat like whenever you feel like. No? Okay, good. So yeah, the actual learning how to write a proof that will come from later classes like analysis, algebra, topology, the honors track, and so on and so forth. And okay, this course is hard. So we we actually beefed up this course compared to last winter, but we can watch you guys how you're doing, and we will adjust if it's necessary. But you should really treat this as like close to like a full-time job in terms of how much time it will take. So that's not to mean that you should be afraid. We are here to help you. Everyone. So the difference between this course and like a Rutgers course is that those guys are getting paid. So it's it's like maybe those professors don't really care too much. Maybe they're just there for the research. But everybody here who is teaching is really here because they want to be able to teach you guys. So we are really here to help you. So if you feel afraid, you feel lost, like please ask us for help. We will help you. But yeah, do try your very best to put in the time it takes to learn this. Okay. Now, as you guys should know, the course will be at 1 p.m. It'll be Monday, Wednesday, Friday, until the very end. And then at the end, we'll have a final exam from Beals. Well, it's not really final exam. It will be just proficiency exam for 300. Um, and then based on that, actually, I'll talk a little bit more later with grades. Okay. And you can see what the contents of the things of the lectures will be in the syllabus, but it won't mean too much to you right now. So yeah. Oh, problem solving section. Okay, so that shouldn't say 4 p.m. in the syllabus. I'll change that to mean 1 p.m. And yeah, I'll try to schedule it so maybe next Thursday on the 30th. But I'll let you guys know for sure if we were doing that. Okay. This is a flipped classroom. I don't know how common it is. Maybe a few of you have actually gone through a flipped classroom, but basically, in the interest of time, like saving time, you guys should review the lectures before class. If you didn't get to review this lecture before class, don't worry. This lecture isn't that hard compared to the other ones, so hopefully you'll be okay. Um, and so I'm very sorry that I didn't mention this earlier. I should have. But basically, you should spend about 1 hour to read the lecture by yourself before class. Um, and basically this allows us to sort of save the time with like you trying to parse a definition that is being given to you, right? You've already seen it now, so now we just recite the definition so you remember it, and now we actually start talking about how to use it. So we'll do some practice problem, and you can sit down and think about it together with everyone, and I think that's a much better use of time when we're all together. LaTeX. So some of you have probably never used LaTeX before, but almost everyone of you should have seen what is LaTeX. So if you don't know, it's basically a way to format math inside a PDF nicely. And everybody who does math uses it at some point in their life. So if you don't know how to use it, go to Overleaf after the class, make an account, and they have some good guides. And you can also copy the text source, like the code that creates the PDF from our notes. It will be on the left hand side when you open the notes, so you can see what line does. Yeah, sorry, I should have
Yes.
said that. Yes, all homeworks need to be submitted in LaTeX. So you should learn it over the weekend and submit it in LaTeX. And you can ask questions about LaTeX too if you're confused. And don't worry if it's like not pretty or whatever. It's okay if it's your first time. Okay, Sangdun like clicks his tongue because he really cares about how people write LaTeX.
I do
It's
care. If I
I
am grading you, I will make comments probably about stylistic choices.
yeah,
But
but don't worry too much. Just learn it along the way. Grades. Okay, so with this, I also want to make another comment, but uh, grades are feedback. So with every deduction of point, we will try to leave some kind of informative comment how it could have been better. And so you shouldn't feel too bad about a low grade, and probably grades will be a lot lower here than you were used to, even if you took 291 or whatever. Um, so more importantly though, don't share grades, please. And along with that, don't try to say that something is easy. Because we really don't need an atmosphere where people are learning something hard and they get to see like people say like, oh, this problem was easy, this took me 5-10 minutes. You can really keep that to yourself. Try to make a supportive environment where people are going to try their best to learn something hard. So please be careful of that. um so grades will also influence what kind of recommendation we give. And it's not grades exactly per se. It is like an overall like estimation based on your homework. So it will not just be the raw grade. Like you can score the same grade as someone else and get maybe a different recommendation. But basically the recommendation will determine to some extent whether BLS will allow you to take an honors course afterwards if you do well enough on the proficiency exam. So for example, if you score well enough on proficiency exam, you will be allowed to take like 311. But based on how much above the base requirement you score on the proficiency exam and the recommendation, you may also be allowed to take 311H. Uh, how much the recommendation matters, we don't know, but we can estimate it's some non-trivial level. Okay. Late policy. So with every lecture, there's a homework. And the problem is that each homework will build on the previous one, especially in the beginning. So we need to get it back to you as quickly as possible, but we also need to make sure that you have enough time to do it. So the way it works will be like this. So let's say you have a lecture. So for example, today you have a lecture on Friday. Then 2 days from now, it will be due at 5 p.m. EST. Okay. So at 5 p.m. EST on this Sunday, homework one will be due. And we really can't like allow like late submissions because we need the graders to give it back as soon as possible. So the graders will only have approximately 32 hours to grade it, which is a really, really tight time limit, especially considering how long it takes to grade these kind of things. So for that reason, we'll have a linear scaling penalty. So like it will maximize at 2 hours. So if you submit an hour late, you will get 50% off as a default penalty, and then whatever else off afterwards. And I know it's harsh, but we really can't make too much exception because I mean we need to respect the graders' time too. They're not getting paid; they're really just doing this because they want to teach you. Okay. And
um,
if you have some issue, yeah, go ahead.
let me interrupt. I don't know if you said this already, but
Mhm.
homework will be done through Google Classroom, right? Did we
Oh
ever send
yeah.
out that link
Um,
or
did
like a meeting?
Contran should have done this, right?
I have no, I don't remember. That's why.
Yeah, it's in lower engine. It's in lower
Okay,
engine.
cool, cool. If you haven't
If
joined,
you're
please join, I guess.
if you're not in lower engine, it's because you're auditing the course. And so you don't have access to it because well, you shouldn't be submitting the homework then. Yeah.
Does zero due to lateness mean it won't get graded?
Uh, Pretty much, yeah. Uh, because like we can't really allocate the time to that, right? Because then if they can't start it on time, right, it's really not fair to them. So yeah. But so we'll have some leniency, like if you really have some extenuating circumstance, like you had 48 hours to do the homework, but half of that like something happened and you just couldn't do it, then please let us know. Let us know as early as possible, and we'll try to work it out with you. Like we were not trying to be mean to you, right? We're not like trying to like be like, oh, like I can't believe you hadn't like. It's just out of respect for the grade. Okay. And last of all, I hate to have to talk about this actually, cheating. So I will not be surprised if some amount of cheating occurs. But basically, what after some discussion, we converged to what most professors would do. So, everything you submit should be in your own words, but that doesn't mean you cannot collaborate. So for example, like let's say, you were stuck on a problem and your friend talks out with you a little, and you get some idea, and then you go and you write a proof. That's okay, and we actually expect you to do that because that is how you learn. But if your friend tells you the idea and then you just go to their LaTeX file and copy it, and you don't know what the hell is going on, then that is cheating. That is 100% cheating. So if we get the idea that, like this is very weird that you wrote the proof like this, it looks exactly like another proof. If we get the idea that something's weird, then I'll pull you at the end of class and I'll ask you to just explain the proof. And then based on that, we'll go from there. But just so don't put us in that position because it's uncomfortable for everybody, and it's really to your disadvantage to cheat in this situation. It doesn't even affect your GPA. So don't do that. And likewise, if you feel like you're struggling enough to want to consider cheating, that it's just easier to copy something, just ask for help. We're all here to help you. Okay. Sorry, Sungjin, I took a lot of time out of your lecture, so hopefully we can still finish in time.
Okay, so that's it, right? Okay, and that is everything that we wanted to talk about. Good, good, good. All right, so I guess it is time to actually begin the material of the first lecture, and I hope everyone is still here. So I'm going to start sharing my my screen. And what I'm going to share is the lecture notes, just slightly modified, so I might be able to give me some space to write if I want to. Not that I will write too much. But the lecture notes are available in what? It is an overleaf link. You should already be able to access it if you would like to follow along. Okay, so here's the right. I'm gonna hope that everyone can be able to see my screen. And the forward is just reiterating what Adam just went over for the past 20 or so minutes. So I'm going to skip it. But you should definitely read this on your own time whenever you are doing the homework and going over the lecture again. All right, so let's begin. So what is Math 300 about, right? Like it's about proofs and it's about statements and it's about proving those statements, right? So let's ask ourselves what actually is like that statement actually is. So our first definition, right, is going to be a proposition, right? A proposition is a statement which is either true, which we can assign a truth value to it. It's either true or false, right? So here's an example: I am a dog. This is false. So we can assign a truth value to it. Sometimes there are clouds in the sky. Is this true or false? Well, it's definitely true because we can sometimes there are times, right? We can just look up at the sky and find clouds or not. The Riemann hypothesis is true. So this is a little bit more interesting statement because we don't know if it's true or false, but it is either true or false, right? We might not know it, but maybe sometime in the future we'll be able to assign a truth value to it. The Riemann hypothesis, by the way, is one of the Millennium problems. So if you manage to solve it, you'll get $1 million. But no one in this world at this time knows how to solve it. So if you're one of those people, then good for you, I suppose. So what is not a proposition, right? These are blue, apricot. These aren't even sentences, right? Code.pdf. This is not a sentence. Maybe another example that that is a sentence but not a proposition would be like, I don't know, something like Adam is tall, right? Is this true or false? What does tall mean, right? Then there's not really no set defined threshold for what tall is. So we can't really assign a truth value to that statement. If it's like vague like that, we can't, where we were not really able to assign a truth value, then it's not a proposition, right? All right. So these were some examples and not examples of what a proposition is. And I don't think I see any questions so far, so I'm going to keep moving on. So here's a note. Sometime you'll see that you'll see some notes or advice as we move along. Whenever you see a definition, it is always, you should almost always, right, construct some kind of example to like sink your teeth into what that definition is, because usually when you have like some definition, especially later on, these definitions are going to get really really abstract, and it might not be so easy to like actually think about what this definition is talking about, right? So it's very useful to have like a hands-on example that you can kind of toy around with. Okay, with that, we're going to move on to our next definition. We're going to talk about a Boolean function, right? So if you've taken computer science already, you already know what Boolean is, right? A Boolean is like a variable, right, that is either true or false, right? And a function, well, you kind of probably already know from like high school math or calculus. I'm assuming that you all probably took calculus. Stop me if this is not true. Is a proposition. So now we're already using that definition from before, whose truth value, whose truthiness, right, may depend on its inputs, right? So for an example, is d of x is a dog, right? So now the statement, right, depends on the input x, right? So if I am saying this, right, then the truth value would be false, right? But if my dog next to me said this, he's sleeping here right now, then the truth value would be true. Okay. So a similar example, L of x would be x loves dogs, right? Again, depends on the truth value of the input, right? And of course, maybe you took multivariable calculus already, but like your function may take more than one input, right? So here, f of x, y takes two inputs. It takes x and y, and we can define it to be x considers y a friend. And depending on which two people you choose, well, you might get different truth values. And maybe you haven't seen this notation before, but this colon equals is notation used to denote that we're defining something. There are other notations that people use, but this is the most common one that I've seen. So so just like for your information, just don't get confused if you see this. I think I heard a ping. Is this a chat or here? Let me check. Someone wants to join the call. Oh boy. All right. So let's keep moving on. So here's the next definition. So we're going to talk about how to so maybe now we have some tools, right? We know what propositions are, and we know what Boolean functions are, right? So we have the building block of a proposition, and we made a proposition now depend on what values we feed it, right? What input we feed it. So now we're going to ask about, okay, if we have different propositions, can we how do we like construct more propositions? How do we like put these propositions together, right? Whenever we have a mathematical object, whenever we have a few mathematical objects, one of the first questions we might want to ask is, how do we combine these things together, right? If we have two functions, how do we combine them together? Can we add them? Can we subtract them? Can we multiply them? And can we compose them, right? Stuff like that. So that's what we're going to talk about next. We're going to talk about conjunction and disjunction. And these are fancy words that basically mean and or, right? But however, a logical and is true when you have two statements. Let's say P and Q, right? And Q, P and Q is true only when, right? If and only if both P and Q are true. Okay, both. But on the other hand, disjunction, right, which is a logical or, is true if and only if at least one of them is true, right? So if P is Q and Q, if P is true and Q is false, then the P or Q, right, it would be true. But if P is true and Q is also true, right, then P or Q would still be true because at least one of them is true. So that is the content of this next note. Excuse me. Because usually when we say or, right, it's usually like exclusive or, right? Where when I say, oh, this or that, right, I usually mean this or that, but not both, right? Like oh, so if someone asks you, oh, do you want pizza or tacos for dinner, right? When you say, oh, what usually when that person is expecting one of those answers, not both, right? But in math or in logic, right, in first order logic or propositional logic, I guess, it means at least one of the options you have, right? Not necessarily both. Are there any questions so far? Good. I think I'm doing decent on time. Great. And
Oh,
already,
let's wait. Hang on. Let's just wait a minute to see if anybody has any questions.
okay, maybe I am going a little fast.
I think you're going at okay speed considering I took so much of your time. But
Right.
if somebody wants to type out a question, it will take a moment.
Um, okay, I don't think
Okay.
I see
Yeah. Yeah.
anything.
Yeah. I think you're
All
good.
right. So already, right, we have a few tools to put propositions together and statements together, right? And it should be noted that already conjunction and disjunction, this is fairly powerful, right? For example, just deviating off of the lecture notes for a little bit, if you have like a bunch of propositions and connect them with like a bunch of ands and ors, and if you ask a computer, hey, can this statement be true, right? This problem is non-trivial, right? It's called the Boolean satisfiability problem. This thing is NP complete, and if you know a little bit of computer science already, you can already kind of tell that this problem is getting hard, right? So already,
Wait. Hang on. You need negations for it to be NP complete.
oh, is it
Yeah.
NP? Is it true?
Yeah.
Yes,
Because
yes, you're right. You're
if
right.
you yeah, because otherwise they're not
We're gonna
related and they
introduce
strongly.
negations later. Yes, yes,
Okay.
you're right.
So
Because we
so
need not.
small.
Never mind.
We need one more
We need
symbol,
one
but
more
then it
thing, and we're
becomes a
gonna.
lot harder.
Yes, you're right. My bad. My apologies. Okay. So, all right. I think. Are we gonna do? No, not yet. So, okay. So now we're going to. Of course. You can string together multiple Boolean functions like the one over here. G of xy is equal to L of x and L of y and f of xy and f of y comma x. And if we are to return to the notation that if you're to go back to the examples we had above, right? G of xy in this case would mean, okay, x loves dogs and y loves dogs, right? Because L, L here we defined above to mean loves dogs, right? And f of xy means x considers y a friend, and f of y comma x, which means y would consider x a friend, right? So they consider each other a friend, and they both love dogs, right? So that's the basic idea of compositions. We can string together and cook up more functions. Okay, but this is just propositional logic, right? We might want to be a little bit more expressive than this. So now we're going to talk about quantifiers. In this case, actually, we're in particular we want to talk about statements that are true about sets, right? Or about either about any element of sets or maybe a single element of set, right? We're going to discuss more about what a set is in the next lecture. But for now, like we're just gonna say like a set is just a collection of elements, maybe a bag with things in it. But that more details will come on later. Okay, so here's the first thing that might be new. This is very new. Everyone know, like maybe you already knew what a statement is, right? But this or proposition is, sorry. But this symbol, this is already like getting, or maybe you knew like what and or were from computer science or whatever. But like this symbol, I don't think comes up in computer science until like way later in your career. This upside down A for all, right? It's an A for all, right? All. This is called the universal quantifier, and people just read it as for all. right? Or for every, or for each, whatever. But that's what it means. For all elements x in a set x, or right, little x in a set big X, f of x is true, right? That's what this universal quantifier means, right? We're going to write for all x in x, this element symbol means in, right? In big X, we have f of x, right? This statement, when you read it out in English, just says for each x inside of the set x, big X, then f of x is true. Okay. So in general, right, when we're trying to make an English statement, we're converting an English statement to a logical statement. You might need to think about a little while about like what about what the variables are, what variables you need to define, and what functions you need to define. Okay. So let's move on. So now we're going to give you an example about converting an English statement to a logical statement. Okay. Here's the example. Bob considers everyone in his class a friend. Okay. So and since we have this word everyone here, right, we're going to need to use the universal quantifier we just defined. And there's no tricks here. There's no like there's only one way to use the universal quantifier. Nothing is hidden. So we're going to define the variable x to be Bob, right? And c, right? C is Bob's class, C for class, and use the function from above. And the function we have above is f, all right? X considers y a friend. We're going to keep coming back to these three examples, so maybe it's a good idea to keep these in the back of your mind, right? So for all people in Bob's class, right? Here we have for all y in C, right? So for all y for people in his class, f of xy is true. And f of xy, as we remember, means Bob, x is Bob, considers y a friend. Okay, so the other quantifier, right, is the backwards e, which we read is which is the existential quantifier, which we read as there exists, right? It's e for exists, and and just like the universal quantifier, there's only one way to use it. There exists at least one x in a set x, right? Such that f of x is true, and we write it like this: backwards e x in x, right? Such that f of x is true, and yeah, that's how you would read it. So here's and we're going to give you another example. Here's an of converting English into logical statements. Among all animals on Earth, at least one is a dog, right? So similar to before, we need to define a set, the set we're thinking about, and think about which Boolean function to use. And luckily for us, right, there was already a Boolean function defined to express this statement. All right, and our statement, right, would be there exists an x in A, right, such that d of x is true. Okay, this colon, by the way, means such that. Okay. Next, we're going to look at even more examples about stringing these together, like composing these together. But before that, maybe someone has a question, so I'll maybe pause for a little bit. Maybe I should check chat. Oh, is there stuff in chat? I don't think I.
Oh, you're good.
Okay. Adam is tall is false, actually. Well, I don't think I can comment on that. All right, next. So we're going to, and of course, a Boolean function itself. When we're composing things together, a Boolean function can make can use quantifiers themselves, right? So here's some examples. There's a person in the class who considers everyone to be a friend, right? So so there is a person in the class already means that we're going to use an existential quantifier, right? So for there exists an x in the class such that everyone, right, who this person considers everyone in the class to be a friend. So for all y in the class, right, maybe I should add a comma here actually. For all y in the class, right, f of xy is true. So x considers y a friend for every y in the class. Okay. Now we're going to change that a little bit. There is a person in the class who everyone considers to be a friend. So there exists a person in the class, right? Making use of our existential quantifier again, such that for all y in the C, so for everyone in the class, right, that f of yx. So notice the difference between these two um, logical statements we have written.
Oh,
The
one
only
sec. Is
is
there
there a
a good
question?
way to remember these symbols? So
E is a
the
backwards E, and A is an upside down A, or
so E
or
is for exist and A is for
yes,
all.
all right.
Yeah.
Was this a question that was
Yeah,
asked?
there somebody asked that.
Okay,
And then the colon would be if you see a colon in a statement, you would say such
colon is
that
such
instead
that
of
yes,
colon.
yes, yes.
Yeah.
Yes, I'm like 90% sure that's why these statements were chosen, right? This is for exists, right? And this is for all, right? I don't know if it's true, but I'm 90% sure it's true, and that's how it was taught to me when I first learned this. So I think that is how I will describe it. Can I go like this? Yes, there we
Another
go.
question. Is there a
Another
difference
question.
between the comma and the colon? There is like a slight semantical difference, but you shouldn't worry about it too much. You
Yes,
can
I
just
think
kind of look at the way that we use it and kind of infer, but it doesn't matter a lot.
like some books I think just use a comma for everything. So like it probably it's fine. You just need that don't be reasonable. Like sometimes when things get too long, you might want to use parentheses also, or actually not here. This I wouldn't use parentheses here. What the heck? I know tools. Maybe I would use parentheses here or something like this, or maybe here.
There was another question. Is the comma to signify then versus such that? Again, don't worry about it that much. Don't worry about it as being like a translation. That's probably accurate enough. But so also another thing is that if you look through the PDF I sent in stuff on Discord, it mentions that you shouldn't actually use uh, shorthand notation when you're doing proofs. You should try to avoid it in general. So this will not actually be a huge problem because you won't be using this language that much. This is just for now, basically.
This type of notation is largely for shorthand. So like when you're taking notes or like when someone is writing down stuff on a blackboard, this using this notation saves some time, right? And sometimes it might even remove some ambiguity. It might actually clear up what you want to prove or what you want to talk about or think about, right? But when you're writing a proof, right, when you're writing a formal proof, which we actually won't do until like I think lecture 3, or when we formally introduce what proof techniques and proof writing, um, you should not, I repeat, like you should never use existential quantifiers or universal quantifiers in your write-ups, right? Um, people, a lot of people, even in 311, have trouble with that for some reason.
Yeah.
Because writing English is hard, but using symbols might not be as hard. But in formal write-up, you should not, or you should stay away from these symbols as much as possible.
Yeah. We have
Um,
another question. Just to
mhm.
clarify, C is not multiplied with F, right?
C is
It
not, so
is not.
yes, I would
We
put a
don't have
comma here.
yeah, we don't have multiplication
Um,
defined for sets and Boolean functions at the moment, and we probably never will. So you
mhm.
can add a comma, in my opinion. You don't need it there, but it would make
Maybe
it
parentheses or a comma, you know what I mean?
in
But
my opinion, the right way to fix that is actually to add like a backslash colon or semicolon or something. That will add more horizontal spacing because I think just having them close together is what is confusing. Backslash colon or backslash semicolon, I think it is in LaTeX, will add some horizontal space.
I think I don't remember what the other thing, because I know backslash comma does it, right?
They're different spacing.
Yes, yes. Is backslash colon? I don't know. I usually put just backslash.
I just mess with them until I get the right spacing.
That's what I do too. Usually I just string them together. But that's not too important. You'll figure all this out as you progress in your LaTeX journey. As you toy around. Are there any other questions before I move on? Are there any other questions about these two examples? Notice the difference between these two examples. The only difference is the f of x comma y and f of y comma x. So the order in which you input, in which you feed these functions, the inputs, matters. Okay, nothing so far. Great. All right, next example. Everyone has at least one person they consider a friend. So everyone, right? Since the sentence now becomes with everyone, now we're going to so for all x in C, right? There is at least one person. There exists a person, right? In C in the class, such that f of xy is true, such that x considers y a friend. So for all x, for each x in the class, there is a y in the class such that x considers y a friend. Cool. Next statement is everyone considers everyone a friend. This means that for all x comma y, so it means for all x and y in C, right? For each x, y, for every x and for every y, this is actually shorthand for all x in C and for all y in C, right? But when we have two of the same quantifiers in the same sets, we can just put them, we can just combine them together because, it saves less space and less work to write. We have f of x comma y is true, so x considers y a friend. So
We
this,
should make a comment here. So let's be really careful about this statement. When we say everyone considers everyone a friend in English, we mean that I'm in a class, and I look at everyone around and I say, okay, they're all my friend, right? But the strange thing in our logic here is that it means that I also consider myself a friend. Exactly. Yeah. So when we say for all x, y, and c, so it's for any choice of x and y, and they can also be equal. So when you make that statement, you should try to refine it if you actually mean that every other person is considered a friend and not themselves. So just a slight subtlety.
it's a very good point. Thank you for that.
Mhm.
And that will be important. That kind of thinking will be important for this next particular example, and it'll come up in your homework. Hint, hint. Right. Um, so everyone has at least two people who they consider to be friends. So notice the word two, right? What is it? So when we say two people, right, we usually mean like two people, two distinct people, right? So we need to be able to express, right, two distinct people in, what is it? Two distinct people, what do I want to say? Two distinct people in terms of our logical statements, right? So here's how we would do it. There exists, for every single x in C, right? Since we have the word everyone here, there exists y and z in C, right? So there's two friends, y and z, such that x considers y a friend, and, right, so now we're using the logical and we have here, x considers z a friend, right? And y and z are not the same. Okay, so this is how we would express like two people. So of course you can kind of extend this idea, right, to three people, to four people, but maybe it might be maybe it might be interesting to consider the case. What if we have like infinitely many people? But we won't really discuss this. But maybe this can we express
Oh, 1 second.
infinitely many in this type of statement? Well, if you want to answer
Um,
that question, you might, and in this case, either y or z could be x. I would say yes.
yeah.
Because I could consider myself a friend, right? There, and that is certainly not a restriction in this English statement, right? I could consider myself a friend, but but the only restriction we have, right, is that that person you chose, right? Y could be x, but whoever the other guy you chose is, that better not be the same guy you chose, if that makes any sense.
Does it make sense to everybody? How that corresponds directly to the sentence in English? Cool. Yeah.
By the way, if you want to think about the question that I posed earlier, you should take a logic class in the math department. Just like a side note, because that's what you actually consider in logic classes.
Well, why can't you just say like you have a set that's
You
infinitely
can define
large?
a set away, but you can I don't think you can never just string together infinitely many logical lines together.
I see. For context, I haven't taken this logic class.
In fact, right? But here's the I will step back and say one more thing. There are statements which we just showed that like well, we didn't show. I just commented that there are statements that you can't express in first order logic. And we're going to, well, and you're going to get an example of a statement that you can't quite express with all the tools, even with negation, which is going to be like the last, or one of the last two examples, last two tools that we introduce, right? Even with all the tools that we introduce here, there is going to be a statement that you cannot express with all the tools that we introduce. And that's going to be in the last lecture.
So we have another question. What is first order logic? Sangjin, we were going to turn this into a logic lecture by accident.
First order logic, I'm sorry. First order logic is, it's basically, it's logic about like, logic is basically all the statements, right? Basically all the statements that we can construct from with all these symbols that we're going to introduce. Does that make sense? Maybe I should have said first order logic. With all, I'll say for all the tools that we introduced so far, or we will introduce in this lecture. Okay.
If you're familiar with programming, you can consider a language to be similar. Like everything I could throw together in a syntactically valid language. I can construct a language from these tools. It's kind of a similar statement. Okay. Oh, another question. Did you define logic in general or first order logic?
No, it is not defined. If you want to think about it, take a logic class. That is Math 461. It is offered every spring. Okay. Sorry for this digression. I might be confusing people. I hope
you're just scaring them.
I'm sorry.
You're gonna make them run away.
I'll stop my discussion. I thought these are very interesting like digressions, but they might be a little bit too like off the path. Does anyone have any question about the examples that we've seen so far? Forgetting all that digression. My apologies. Anyways, kind of conversion. All right. I'm going to assume that those comments are not related too much, so I'm going to move on. So okay. It's okay to combine adjacent quantifiers so long as they both use the same set, as we did here, right? I wonder what this color does. As we did here, as we did here. Okay, it's fine. It is shorthand, of course, but everyone kind of knows what that means. All right, so next definition, right? Negation, right, is negative, right? As when we flip a positive thing to a negative thing, right? So it flips the truth value, the truthiness of a proposition. And the symbol we're going to use is this, what is the symbol called? This crooked line, I guess.
I don't know if it has a name.
Yeah. Some books, no, like if you're following like another book, some books will use like this, but we're going to stick with this because that is the superior notation. And that symbol is also kind of overloaded, as in the fact that it's used for like 10 other things. But this crooked line, is only used for negation. So we're going to stick with this. Yes. Okay, so now we're going to think about negating propositions, right? So we're going to, one of the first questions we might ask is, how does negation act upon all the symbols that we've defined so far? We've defined the existential quantifier and the universal quantifier and the logical and the logical or. All right, so first we're going to introduce how negation affects the quantifiers. Okay, so if we're negating a for all statement, right? Then we're going to get, so we flip the quantifier, right? For all becomes there exists, right? And we negate the inside also, okay? And like as a symmetrically, is that a word? Analogously, if you negate an existential statement, right? Then so if we negate not, so let me read this. Not for there exists an x in x such that f of x is true, then we're going to flip the quantifiers and negate the inside. So we're going to get not there exists means for all x in x, right? Not f of x is true. Now this is when I first saw this, this was a little confusing to wrap my head around. So I wouldn't be surprised that there might be a question. So I'm gonna check. I don't see a question. But but you should ask yourself, you should convince yourself, right, after this lecture maybe, why this thing is true. It's a little tricky to wrap your head around. But the idea is that if it's not true that a statement is true for every element in the set, that means there's at least one guy in the set that is a counterexample to that statement. And if it's not true that like there exists a guy in a set that satisfies a proposition, then it's true that for all guys in the set, then the proposition isn't satisfying. That's basically the explanation that I can give you.
If you weren't able to follow that, don't worry because it actually is tricky, but you should like try and sit down and like reason it out.
Yes, you should sit down after class. Again, as we maybe it's worth emphasizing again that like this Math 300 is not easy, and we will expect a lot of time to be put into to be put into understanding all this. Okay, so next thing, right? So now we found out how to negate quantifiers. Let's think about how do we negate the and the or. Okay, and it's kind of like the distributivity laws, right? These actually have a name. These are called De Morgan. These are called De Morgan's laws, right? So if you negate an or, right? If not P or Q, right? That's the same thing as not P and not Q. And analogously, we have not of P and Q is the same thing as not P or not Q. Okay? And same as before, this might be a little bit hard to convince yourself, right? So you might want to sit down at the end of class after class to really convince yourself that these things are true. Okay? So now let's take the examples that we constructed above, right? These examples. I think these are the same examples. Yes. And actually, let's try negating them. Okay? And you'll get a lot more practice with negating statements in your homework. So the general idea is going to be just flipping everything. Excuse me. To negate statements, we're going to be flipping things. So in this example, right, if we negate this entire statement, right, then we're going to first flip the quantifiers, right? The flip the exists to an for all, right? And then flip the for all to an exists, and then negate the inside, right? And let me just write out the next particular example, right? If we have this, I think I have time, right?
Yeah, we have time.
Right, such that f of x, y, right? If we have this and we're trying to negate this, first I'm going to flip the first quantifier I see, right? There exists an x in C, right? Such that, okay, I'm going to flip the next quantifier I see for all y in C, right? Such that not f of x, y is false. Okay, and that's exactly what we have here. Okay, great. I'm going to move on to the next statement. This one's a little bit more tricky. Oh my God, something happened. So this one's a little bit more tricky. We're going to negate like we're going to negate the next statement, and this is the last example that we did above. Yeah, I still have time. I'm going to write this down. I think this is worth writing down. C such that f of x comma y and f of x comma z and and y, what am I doing, is not equal to z. And y is not equal to z. So we have this now we have this chained and, right? So now let's negate this. So when we negate this, we're going to flip the first quantifier, right? There exists an x and c, right? Such that we flip the next quantifier for all y and z in the class, right?
So just
I
small
should
note.
use that colon here.
Um, so we have these two variables like instantiated right next to each other. But since they're both under the same quantifier, we can just flip them simultaneously. So it ends up being the same thing.
Right. If you were to write it down, write it out, it would be y in c, right? Such that z in c, right? But if we would write it out like this, but if you flip them, it's going to be for all y and c, for all z and c, and that's the same thing as we have over here. Cool. And now we're going to flip this chain of ands. And to flip this, it's the same thing as we're going to flip all of them at the same time. So we're going to get not f of x comma y, or not f of x comma z, or y is equal to z. So let's think about what this statement means. What did this statement, the original statement meant everyone has at least two people who they consider to be friends. But the not of that, right? The not everyone has at least two people they consider to be friends is okay. So there is at least one person in the class, right? Such that for all all pairs in the class, right? Either x does not consider y a friend, or x does not consider x a friend, or y is equal to z. What does this mean, right? That basically means that there is at least one person in the class that does not have two people who they consider to be a friend. Okay, and that's what this and this for all, right? And this is a little non-intuitive, but this for all runs through all different pairs of people in the class, right? So this statement is actually equivalent. That might be actually you might need some time after class to think about that a little bit. Okay? Is everyone okay with this? Oh, I heard something. Oh, okay. Someone raised a hand. How do I open queue? Lower your hand. I can lower your hands. That's
Why?
very cool.
Why?
All right, but what is
Why?
your question?
Oh, I
Lower.
just wanted to say hi, sorry.
Okay. Is there anything in the chat? L not. Um. Okay. So someone brought up L
Wait.
not. Huh?
Oh,
Is there a question?
we have an actual question.
Oh, the colon is used as a such that, right? And we only kind of say such that after an existential quantifier, if that makes sense. That's it's not a Q.
Let me clarify something. I think you guys are thinking you have to have these things here, so you're trying to figure out the rule. You don't need it there. These are just kind of like syntactical sugar. So like if in your homework you just don't use colons or commas or colons, it's perfectly valid. Um,
Oh, I
we
would
just
prefer
use it.
use at least use commas, please.
Okay, sure.
It does not help, like, because it harms readability, if that makes sense.
Okay.
And shorthand is used for ultimately for you to be read, right? So at least use commas. Colons, I would argue, is syntactical sugar. Yes, that's true, but um, at least use commas, please.
Okay.
It's
But yeah,
it's hard to grade if you don't have like these if you write a sentence without any spaces, right? Then who can read that? You know what I mean?
but yeah, really don't worry too much about it and you'll like
Yes,
infer the
it's not
rule
the
if
end
you
of the world, but
yeah.
for readability. Oh, it's not a question. I call that symbol L not because it's L not in tech. There was a discussion about what it's called. Yeah. It's L not, or I think also neg works. Neg gives you the same thing. neg for negation, so whatever, or negative. Any other questions about negation so far? This is going to be the
Wait,
okay.
also real quick, did we explain that we're writing the LaTeX next to stuff?
It's in the notes. I mean, yeah. I mean, I didn't say it because I'm not going. I
Oh,
don't want
okay.
to explain LaTeX as in the lecture. But yes,
Okay, yeah, yeah,
this
yeah.
is LaTeX. This thing in the text TT. What's the Is this sans serif? Yeah, sans serif font. Sans serif? No, it's not. What's this font called? Like
I
in
don't
like Microsoft,
remember.
it's like Courier New or something. But like I don't know what this type of font is called. But like in this type of like Cody font, right? Code E. This is the LaTeX code, LaTeX commands. If you have questions about what we're typesetting, either ask in the Discord or just flip through the lecture notes and to see if it's there. Um, is that okay?
Ooh, we have a hand
I'm
raised.
assuming that I'm assuming that you are also following this.
Yeah.
Is it Carrier? Oh, it's monospace. Thank you. Computer Modern is the serif font. It is the default font. Someone Courier how do you pronounce that? Carrier? Courier? Look, I've never said that word. I just say mailman. Come on, man. All right, someone has raised their hand. Winston, what is your question? I'm gonna
I have
lower
a
your hand.
question on negation.
Sure.
Could you just go back to the notes? I want to ask.
Hmm.
So when you negate, like, or like, go to like the dog example, right? So if I were to negate that, like all, how do I say, like,
Which statement is the dog?
let me just pull up the notes, have it
I
open.
think it's like the first thing, right?
Yeah, like one of the
X
first
loves
thing,
dogs or
or just like anything,
dog
any
considers.
dysfunction. I just want
Among
to
all
ask.
animals on Earth, at least one is a
Yeah,
dog.
yeah,
Is this
sure.
thing?
Yeah, so if I were to negate that entire like statement, right, or proposition, I suppose, right?
Yeah. Hmm.
So it would become for all of x in A,
Hmm.
and then not is it not d of x is false or true?
No, it is. So d of s, d of so for all x and a, this part is correct. You would get d of x is false, right?
Right.
So that would mean not d of x. Does that make sense?
So yeah, so not d of x is true, right?
So
And
yeah. So like if we're to read
Sangjin,
this, if we're,
Sangjin, the reason he's asking is because you like in somewhere else where you negated it, you said like not like something of X is false.
oh, did I say
yeah.
that?
So
That's my bad.
yeah, you
Oh,
like
okay,
double
okay.
negated yourself. Yeah, no, that was just like weird blip. Yeah,
Okay, yeah,
That is
I
like
understand.
that was a verbal mistake.
yeah.
Got it. Thank you.
Stop me if something like that happens. But thank you for catching that. So if we were to unpack this statement, it says like for all animals on Earth, right? For all X and A, X is not a dog. Okay, and that's exactly what we exactly what we expect when we negate this universal existential quantifier, right? Sorry, Catman. Catman. Wait, what was? Okay, I don't know. Something happened. Someone messaged me something, and I have no idea what's going on. Makes me feel like a boomer, which is terrible. Okay, we're almost done. So the last tool we're going to use is the implication, and I believe this is arguably the most important tool that we're going to have in our toolkit because almost every proposition you see in upper level math courses is going to be an implication. Maybe Adam disagrees, but I don't think he will because I think I'm right.
You're right.
Okay, so this implication, right? And note that we're going to use a double arrow here, right arrow. If you want to be weird, you can also use implies, but this gives you a longer arrow, and I don't think Adam likes that. um,
It's not that I don't like it. I honestly don't really care.
so what's this is going on is this thing is true, right? As long as Q is true whenever P is true. So this you read this as if P then Q, right? So note that like if P is false, right? If P is false, then we don't care. This is something that I think we should note. If P is false and Q is false, the implication is still true. And if P is false and Q is true, then the implication is still true, right? The only time when this implication is false is when P is true and Q is false. Then we say that the implication is false. Okay. And our next note, we're going to use a double arrow for implication because a single arrow, right, has other uses. Most notably, it's used in limits and convergence, which we'll come back to later. I can't think off the top of my head what this thing is used for. Maybe it's used for graphs, I think. I don't remember. But my go-to answer is for sequences and convergence. Okay? And we don't want to overload symbols more than we already have to.
Yeah.
Are there, maybe Adam has a better example. What's this thing used for?
Well,
other than limits?
It's mostly like when we just say we're mapping from one domain to another.
Oh, right. Yes, functions. That works too.
So like and just like categories.
Oh, I don't really. Yes. Functions.
You don't fiddle with that stuff. You're too good for it.
Oh, I don't.
Okay,
yes, category. Cat theory is abstract nonsense. Someone has raised their hand. Open queue.
Yeah, go ahead.
Yeah. For that one statement, P implies Q. Would that entire thing still be true if, let's say, if P is false but Q is true? Would the entire statement still be true?
I think implication is the one instance where a truth table might be important. So I'm gonna do it.
If you do it, I'm firing you.
So you said if P is false, right? Right? And Q is true.
Mm-hmm.
Then if we put them together and then P implies Q is true. The idea is when P is false, then there is no promise being made. And so we don't really care about the entire implication.
Oh, wait, I want to amend that slightly. Okay, so this statement P implies Q itself is a promise. So like imagine like I'm like running a stand, right? And I tell everyone like, hey guys, P implies Q. So basically like if someone comes up to me and they give me P, I have to give them Q. And if I'm not able to do that, then I've failed on my promise. I've like told a lie to everyone. So like if nobody comes to me and gives me P, then it doesn't matter whether or not I have Q because I didn't actually technically fail on the promise. So that's what P implies Q means. It just means as long as you can produce Q. So in this case, since P is false, it doesn't matter what the value of Q is.
Okay, that makes sense. Thank you.
We're going to come back to this idea in lecture 3, I think. Yes, we'll come back to it later. I think I heard another ping. Something happened. Someone raised their hand. Volpo, I'm gonna lower your hands.
Yeah.
Yes. What do you want?
I have a question with negating P implies Q.
Ah, yes, we're gonna get to that, but yes.
Oh, okay. Because I was just.
Do you want to wait until we?
Sure.
Do you want to wait until we get to it, or do you want to ask now? Okay.
I'll wait.
Is there anything else in the chat that I might wanna pay my attention to?
No.
Okay. If 1 equals 2, then 3 equals 4. Yes. We'll get back to that in lecture 3. All right. So, this is the one last tool we have, right? How do we negate something? We can negate something like this. Right. This is what I said. Implication is false precisely if P is true, yet Q is false. So when we negate this thing, right, we have P needs to be true, right? And Q needs to be false, right? So that's where the negation comes from. So that means if you negate it again, right? So if you negate both sides and use de Morgan's law, P implies Q is the same thing as not P or Q. So notice, right, that if P was false, then as Adam said before, there was no promise in the first place, or the promise wasn't broken. So we don't really care. The entire statement is true. And if Q is true, right, then we don't really care. The entire implication is true. Okay? That is the content of this paragraph. So does anyone want us to reiterate what was said there? That might be a little bit
Yeah, I'm wondering.
I think that example is something we're going to come back to in the third lecture. Did someone say something?
Yeah.
Yeah.
Okay.
I still want to ask about the negating P implies Q, because I think I'm just like processing it as though P and Q are Boolean functions themselves.
But
because it's like
how we are written, they can be, yes. They can be.
But like if
So-
they are actual statements then, and then you have like they both evaluate to either true or false, then like the implied part seems kind of strange because they're each true or false on their own.
So we want to be a little bit careful about context, right? So like let's say P and Q are basic statements, right? So let's say they're literally just true or false. Then it's very clear whether the implication is true or false, right?
Mm-hmm.
But now let's say they're a Boolean function, right? So let's say, for example, I say, if it is raining, then the ground should be wet. But let's add a little bit more context here. Let's add a variable which represents a time. So like if it's raining at time t, then the ground should be wet at time t, right? So now I can talk about this implication, and I can talk about, is it true, like for example, for all times t, or is it true for some time t, or something like that. Right, so it can be context sensitive whether the implication is true when you plug in a certain variable into these functions now.
Okay.
Right now, note that like we're just dealing with, oh my goodness, what just happened? We're just dealing with P and Q, right? And we're just letters. They're just letters, and it's very abstract right now, right? We've abstracted out like everything that we want to talk about. I think like as we move on and we get more things, and these variables are like replaced with more concrete things, like sets and graphs and functions, it'll be a little bit more easy to sink your teeth into it. So I wouldn't be, and especially in your homework, you'll have an opportunity to sink your teeth into dealing with these things. So I wouldn't worry too much if this is confusing, because this thing is confusing. It's very abstract. So yes. Are there any other questions that I might answer? Don't be scared. Okay. Let me check chat if there's people here. What?
They're just being mean to me.
I'm not gonna.
They think because I like Among Us that they can say whatever they want to.
Maybe I should just stop checking chat to look at all this degeneracy. All right, so now we're going to put this thing together. The if and only if is the last tool that it's the last tool we can make out of the tools that we have. It's abbreviated as if and only if, IFF, if and only if. If you actually like look up IFF on Google and press on that volume like speaker button, it'll say if and only if. Like that's how you pronounce it. It's pronounced if and only if. Okay. I don't think this might not be said, but this symbol is, I think, is a left right arrow, something like this or something like that. It's also IFF on LaTeX. Okay. \IFF, but I think this might make it a little bit longer. It's the same thing as P implies Q is true and Q implies P is true. Okay. Okay, so the if, wait, hold on. The if part, well, that's not important. The if direction is this direction, I think, and the only if direction is this direction, I think. Something.
We don't need to go so much
that's
into
not that's not very important. Okay. All right. Last thing. This is just a different way to phrase implication. We say P is sufficient for Q if P being true means Q must be true, right? So in other words, P implies Q. and P is necessary for Q if P cannot be true without P, or Q. Did I say that correctly? Q cannot be true without P, right? So that means Q implies P. Okay, this is a little. This might be confusing, right? But but you'll see these two words in this context the most, right? In the next context, P being a necessary and sufficient condition for Q, it is the same thing as just P if and only if Q. Okay, and that's usually the context you'll see these two words in math. And okay, that's basically everything I wanted to talk about for this lecture. Does anyone have any questions? And we are doing fantastic on time. Is equiv equivalent to left right arrow? No. Equiv, right? Equiv gives you this. And it's similar, but it should be used in a different context. And left right arrow, I think it's this, or I'm gonna say if and only if, gives you this. Was this your question? These give you different symbols in terms of logic.
Yeah, semantically.
Semantically, I
so
think they're different.
I mean, they are the same, right? But
Well,
like
they mean the same thing. But in context, when I think of it, I think of them as different. If that makes sense.
Yeah. So the difference would be like equiv. You would use it for like logical equivalence, right? So, like if you were doing some logical manipulations, like let's say you applied De Morgan's law or something, then you would put equiv and then say what it's logically equivalent to.
Oh yeah. I think the correct word is syntactically equivalent versus semantically equivalent. I think. All right.
Mm-hmm.
Yes. Anyway, maybe I think you will get a better idea of what we're talking about. Yeah. So that's like a very trivial if and only if is like syntactically, right? But if and only if requiring proof is like it depends on like the values of P and Q, if that makes sense. So this would be syntactically, right? And this would be semantically. Does that make sense? Take a logic class, take the math logic class if you want to know more. So I think it's interesting stuff. It's just that sometimes it can be very abstract nonsense. It's really hard.
Yeah.
Magician's
Okay.
Are there any other questions?
Oh yeah, we should ask questions first. Sorry.
Are there any other questions that we might entertain? Of course, if you run into questions after, you can just shoot. You just ping us on the server. That's what that's there for. Okay. So what is it? Your homework, right? You have homework. It's on that overleaf. It's in the overleaf document you can find in the What channel. This entire lecture notes without my lovely annotations is there too. So you can always reread what you wrote, if that makes sense. Or does that make sense? Reread what we went over. Are there any other questions?
So I have a short Google Forms for you. It's like an exit survey. It's just literally just 2 questions. Like, did you get to go over the notes before class, and how did you think about the pacing? Please answer before you leave. If you are not an instructor or a grader, or myself. And there's also another thing for comments. If you have literally any comment, like you didn't like how he was writing on the screen, or something wasn't clear, it was hard to read, literally anything, just feel free to write it. It's anonymous. I can't see your email or your name, so you can write whatever. So please fill that out.
I'm going to stop the recording right now. How do I stop the recording? Stop recording. The recording will be posted